Alrighty, 8.10 buffer capacity, the last section of Unit 8. So, let's talk about it. So, obviously, we know about buffers by now. At least you should, theoretically. And as a reminder, buffers are trying to not change its pH, it's trying to prevent it, even though it's stress. And so, a buffer capacity is talking about how much hydrogen or hydroxide that can be added to a buffer and how it will not change its pH. So pretty much buffer capacity is very, very similar to buffers themselves because obviously we're talking about buffers. And so you're looking at the ability to handle the stress of those additions to the buffer. So how much of those various H pluses or OH minuses that can be added. And so in the last section, we learned about pH and how the pH of a buffer solution is based off how much of the conjugate base in the weak acid, or if it's a weak base and then it's conjugate acid instead. So, depending on which situation we have. So pretty much this ratio was from the last part of the HH equation. And so, the negative log of this part that I'm showing right here. And so, again, you could do this for both a conjugate base and a weak acid or a conjugate acid and its weak base. And so capacity of a buffer is, as I have highlighted here, based off the magnitudes of the concentration of the conjugate and its original form. Again, weak acid and conjugate base, or a conjugate acid and its weak base. So, weak acid, conjugate base, weak base, conjugate acid, tomato, tomato, depending on your situation/buffer. So pretty much the capacity is the limit of what the buffer can actually do. So let's go over an example. So we're going to calculate the pH of both of these situations. And so I shorthanded here. I didn't write the acetate ion because I wanted to just shortcut it to emphasize more of the problem rather than the molecule itself. And so here acetate is AC. And sometimes textbooks and other resources use that too. But again, acetate is just CH3COO minus 1. So I'm just not showing that. So we have our weak acid part here. This is the acetic acid. And then we have the salt here, the NaAC, and that has the conjugate base because remember, sodium is dissoluble in solution when it is ionic, and so we memorize that one solubility rule, so that's why that is the conjugate base because it has the AC minus, the acetate ion. And so this is definitely both buffer systems because we have, again, a weak acid and its conjugate. So that makes sense. Cool. All right, so we're going to go ahead and calculate the pH of each system. So we're going to use the HH equation, which is right here. And so both of these systems are acetic acid, so I'm just going to use the same Ka for both of them. So I'm going to plug it in. Once I plug it in, I get my pH there, and I get my pH there. And so notice the pH is the same for both of these. So just like the previous slide says, pH is determined by the ratio in the HH equation, which is right here. So that's why the pH is the way it is. So again, pH is affected by the ratio of the conjugate and its weak acid or weak base, depending on which system we're talking about. So in this system, we are specifically talking about the weak acid known as acetic acid and the conjugate base, the acetate ion. Cool. Now, let's look at the magnitude of both of these. So if we go back to the previous question, the pH was both, right? So there we go. And so let's do a quick little mini your turn. What is different about these two buffer systems besides it's 5 versus 0.05? So think in terms of reality, if I had both of these in solution, what is different about them? So think about it real quick. Alrighty, so what's different about them? Well, let's say we had the same amount of volume in both of our containers that they're held in. That means the number of moles is what's different about these two buffer systems because remember, molarity is moles per liter. And so we have 5 moles per liter versus 0.05 moles per liter. And so buffer A has more moles of the acetic acid and its conjugate base versus buffer B. So that is what's different about them. All right, so let's say we added some hydrochloric acid. As a reminder, hydrochloric acid is a strong acid. So we added a specific amount, whatever that specific amount is. And so in the first buffer system, the pH was 4.74. In the second one, if I added the same exact amount, then the pH ended up being 4.56. So based off the results happening here, which one has a better buffer capacity, A or B? Think about it for a second, and then I'll talk about it. Alrighty, ready? Cool. So in the first system, we had the pH, it started at 4.74, it ended at 4.74, so it didn't change, versus buffer B went from 4.74 to 4.56. So that means that the first buffer was really good at being a buffer. Remember that a buffer is trying to not change its pH, so buffer A is the better buffer. Now, why is that? Well, we're looking at the magnitude of the amount we have. And so, as a reminder, we're looking again at the molarity, but specifically, what was different about them is we were looking at the number of moles. So the moles of the first buffer had more moles of weak acid and more moles of its conjugate base, versus buffer B had less moles of both. And so when you have less moles of things in your buffer, that means you have less reactions that it could neutralize a stress. And so the better buffer capacity, again, is the first buffer system, buffer A, because it can absorb more of that stress, pretty much more of that strong acid. And so, again, magnitude is what's important to know how it's going to get, how the buffer specifically is going to get affected by this system. So if I had this as an FRQ question, I would say the first buffer system is better because it has a higher magnitude. The higher concentration of the weak acid and its conjugate base means there are more moles that can help neutralize the added stress, in this case, the strong acid HCl. So that's what I would say for an FRQ answer. Cool. All right. Bonus question. What part of the buffer is neutralizing the added HCl? So check real quick. Alrighty, ready? So the part of the buffer that's neutralizing the HCl would be this guy, the conjugate base. The conjugate base is going to act like a base. It's going to grab the H, because that is the part of the strong acid that it can interact with, and then that's how it neutralizes. And so that's why in the first buffer system, it stayed at 4.74, even though we added a strong acid, because there was enough moles of acetate ion to neutralize that H from the hydrochloric acid. So that is why. Cool. All right, here is an MCQ. This is actual MCQ, so read this to yourself and try to pick the best answer. So pause the video and try it out. All right, ready? Here we go. So I decided to highlight some stuff. Now, anytime you're taking a test, you should be doing something like this. Now, obviously, you might not be allowed to use highlighters on a test, but for me personally, when I took tests, I would always underline or do certain shapes on tests or whatever. And so in this case, I'm using color because I'm doing slides. But if I were to take this as an actual test, I would do, for example, underline what I had in red and then put like a star next to it, and then underline the stuff in blue, and then put like a square box or something. That way I can determine which parts are related or like similar to each other. That way you don't have to keep rereading the question. That's one of the things that people get caught up on when you have longer questions like this, is that there's too many words. Well, highlight or bold or underline or something so you don't have to continually reread the question over and over. So that's what I did. And so looking at the things the student needed to do versus what they accidentally did, in the let's see what's different about them. So in the red parts, we have 250 milliliters, so that's the same, but the molarities were different. It's 0.1 versus 0.05. So we see that the molarity was cut in half from the mistake. And then from the base, or the conjugate base rather, we have 500 milliliters versus 250. So that was halved, but the molarity is the same. And so in green here, I wrote that down. I also talked about what that meant in moles. I didn't show my math work because I didn't think I needed to, but if you want to prove that to yourself, you can take the liters of this and then multiply it by the molarity to get the moles versus the liters of this and multiply it by the molarity, and then do that for like everybody on here, and you could compare the answers. But essentially you have half the moles of acid and half the moles of conjugate base. And so for C and D, we're talking about capacity. Well, in this case, we're lowering the capacity because we have half the moles available. Think about the example from earlier. So that's why we're eliminating C and D. Choice B is talking about lower amounts will lower pH, but the moles of both were lowered, so that doesn't make sense. If I think about the HH equation, you think about the second part where it's negative log of the conjugate divided by the weak acid, it would be the same because half versus half. So it's still the same as if they didn't make a mistake from earlier. And so choice A makes the most sense because it's lower capacity because, again, you have less moles of both the weak acid and its conjugate base. And so since we have less of them, that's why choice A makes sense. There we go. Cool. All right. So how do we choose a buffer? Well, we just go based off the definition of a buffer. So we're trying to find the buffer that helps resist the change of pH, because that's the point of a buffer in the first place. And so what we want to look at is the ratio of the conjugate with its weak thing. Again, if it's a weak acid, it's conjugate base. If it's a weak base, then it's conjugate acid. So if the ratio is 1, where you have the, both of them equal to each other, like so, like I said here, then pH equals pKa. If I take the HH equation, the second part of the HH equation, which is the ratio here, log of this, it equals 1, and so when I put log of 1, that equals 0, and so that's why pH equals pKa. And so you want the most effective one by looking at the pKa and seeing how close it is to the desired pH, so whatever pH you want to get to. And so some example MCQs or FRQs you could get is you would get a list of potential acids and bases. You would get a list of their Ka values or their pKa values, depending on what the table has. And so from there, you would need to compare it to the pH that you are trying to keep. Like, what pH do you want to try to stay at? So here's an example. Here's an equation. Here is a question. So go ahead and read that question to yourself real quick. Alrighty, ready? Let's break down this problem. So we have hydrazine, which is this formula. We have a Kb value, so that means it is most likely a weak base. And I reconfirmed that by looking up here. So I have this, I have water. I notice that the hydrazine is grabbing an H from the water, so it indeed is acting like a base, so that makes sense. I'm given a Kb value. And so we are trying to prepare a buffer to 8.20, and so we're going to use the, what is this called again? Hydrazinium. Yeah, so we're using a hydrazinium, which is the conjugate acid of the hydrazine, because it's the NH2NH3 plus, the ion part, and then chloride is just going to chill in solution as a spectator. And so before I actually talk about this problem, two things. First, a side note. If you work in a lab, you have different purities of certain compounds you're working with. So for example, we have a 85% pure hydrazinium versus a 99% pure hydrazinium. And so what the heck are those percentages even? It means how pure is your stock solution of this thing. So if you have 99% pure, that means it will barely, if at all, have any impurities in it. If you have 85%, that means 85% of it is good, 15 or so has some impurities in it, but that doesn't mean it's bad. It's cheaper for sure because it's very hard to purify things. And so 85% would be way cheaper compared to 99%. Context is very important on deciding whether you need to do 99% pure versus something that's a little less pure. And so this is for if you work in the lab in the future, whether an internship or something. So you always want to ask your PI, which is the principal investigator, whether or not it should be very pure or like you can skimp out a little. It purely depends on context because 85 again is cheaper compared to 99%. So it really, really depends. So FYI for your future lab experiences. All right. Second thing I wanted to talk about is let's prove a point first. So I want to prove the point of the last slide real quick, the one I just went over before this example. So I'm going to take the constant equation sheet equation here, right? And so I can solve for Ka. I get that. Cool. We're assuming this is at room temp. So that's why I'm just using the Kw that was given on our constant equation sheet. And so I can calculate my pKa, which is 8.23. And so notice the pH that we want to get to is 8.20. 8.23 is pretty close to 8.20. And so that's why we're going to use this as a buffer because, again, the Ka value, or the pKa value, is close to the pH value. And so that is why this hydrazine slash hydrazinium buffer system is going to be used to try to get to this pH. Because again, we want to get as close as we can to this pH by looking at the pKa. So that is why. Cool. All right. So we're going to go ahead and actually do the problem. And so we're looking at the capacity of the buffer. And so how does this error affect the pH? So this would probably be like an FRQ question. So notice that the conjugate acid is being affected because this is a conjugate acid. It can donate an H here, and so that's the equilibrium where we're going backwards. And so that's why it becomes water and the hydrazine once again. And so the amount of the ion, the conjugate acid, is being affected. We have less of it. So in this case, again, we have less of the conjugate acid, and so that means we have less magnitude. We have less moles, okay? And so capacity is less because we have less of moles of the conjugate acid, and so it'll be less effective. And so pretty much if I have less of anything, so in this case, if we had less of the weak base, or if we had less of the conjugate acid, or vice versa, if we're thinking about the other kind of buffer system with a weak acid and its conjugate base, then that is going to affect how good the buffer is at actually being a buffer. So again, capacity is less because you have less moles, in this case, of conjugate acid. So it will be less effective as a buffer. Less stuff, less capable. Cool. So if we were to look at the HH equation, we're pretty much affecting, for example, here, I can look at acid on the bottom, right? And so if I were to think math-wise how this is, this is being affected, well, I could plug in random numbers and see what happens. So pKa doesn't change. So the pKa given from the previous point I made last slide was 8.23. And so if I affect the acid part of this HH equation, I am affecting the denominator. So the denominator gets smaller, like 4 versus 3, for example. So if I take a log of a number that's less than 1, because if the base was like, I don't know, 1, for example, then if I take the log of that, then you'll have less negative number. So what the heck am I talking about? Let me write this down. It'll make more sense if I do. So we don't have actual numbers in this. Well, we kind of do, but I'm not going to use the real numbers on here. So pKa was given earlier. We have 8.23. And then let's say the base was like 1-ish. I'm just estimating for the sake of showing a proof of something. So the original 99%, let's say that was 4, right? And then because it's 85%, you have less moles of it. So let's say it's just 3 instead. So we're looking at these two situations. And so if I take log of 1 divided by 4, that's about negative 0.6. If I do log of 1 divided by 3, that's about negative 0.47. And so my, again, pKa was 8.23. So 8.23 minus 0.6, that's going, I'm going to number these like 1, 2. So 1 over here. So if I take 8.23 minus 0.6, that's going to make my pH equal 7.63 versus number 2. If I do that same calculation, 8.23 minus 0.47, that's going to make my pH 7.76. And so if you're looking at these numbers, well, you can see how the pH is changing based off the amount you have. So you have, for example, again, this number, and then the pH increase. I'm just showing like kind of the logic of the explanation I said out loud. You don't actually need to do any of this math. So if you're like, I don't get what the heck you're talking about, just understand what's happening to the capacity, and then that's all you really need in the explanation part. Yeah. Now, obviously, if you're given concentrations of stuff, you could calculate that, but I don't want to because it's not part of this problem. All right, cool. So this is straight up a screenshot from College Board, so I didn't change it at all. That's why it's kind of blurry, because I just screenshotted it and then blew it up in a bigger size. So this summarizes what I just talked about in this section, so make sure you understand what this is talking about, and if you have questions, make sure to ask me. Okay, so we're going to end on one more MCQ practice. So read this problem, look at the different answers, and then I'll give you the answer in a few moments. All right, ready? Here we go. Bam, it's A. I didn't explain my answer thoroughly compared to the previous your turn because I got lazy, I'll be honest. And so A is correct because the buffer capacity depends on the concentrations of the weak acid and its conjugate. So the lower concentration of both of them means the lower buffer capacity because there's a smaller amount of moles. B is incorrect because it depends, again, on what I said earlier. And C and D are also incorrect. I don't know what else to say. Make sure you know the difference between capacity versus just pH in general. Going back to the very, very first slide. So let's actually go back to the first slide real quick. So let's go back. So here's the first slide. pH is based off the ratio. As we saw in the first example, the ratio of these could be very different in terms of the amounts, but as long as they're the same, they can calculate the same pH. Versus how many moles you have of both of these based off the concentration will determine the capacity. So be very careful about that. It is very, very easy to confuse what is determining pH versus what is determining the capacity of the buffer. Alrighty, that is the end of Unit 8. Yay! Bye!